Okay, so in the previous video I spoke a bit about coefficient of restitution, that it allows us to determine the velocities after impact. It allows us to determine how much energy we've lost, and we'll get to this derivation. But what we want to do first is introduce that we can either get central impact, okay, or oblique impact. Central impact is just simply the line of action basically passes through. Let's read here. It occurs when the direction of motion of the mass centers of the two colliding particles is along a line passing through the mass centers of the particles. This is the line of impact. Okay, so the line of impact is something that's always perpendicular to the plane of contact. Okay, so if we've got these two particles contacting each other, right, there's the plane of contact, and the line of impact will always be perpendicular to that plane of contact. So we've got central impact if these mass centers are moving along this line of impact. We've also got something called oblique impact if there's an angle to this line of impact. Okay, central impact, oblique impact. I hope I didn't confuse you too much there. Okay, now let's have a quick look at central impact. And remember, we're trying to get to the point where we derive the coefficient of restitution. Okay, we want to derive the coefficient of restitution. So say now we've got two particles. This particle A, as you can see here, is moving at a higher speed, higher velocity than particle B. It's moving towards particle B, which means they will eventually collide. All right? Okay, so that's step one. Velocity of A higher than velocity of B, moving towards B, they will collide. Now they collide and they begin to deform. And as they collide, they have these internal deformation impulses called integral of P dt. So A on B is applying the impulse plus integral of P dt, and B on A is applying an equal and opposite negative integral of P dt. Okay? But what you need to know is that they're still moving toward each other because they're still being deformed. Okay? Then the next step is that they have maximum deformation. Both particles have maximum deformation, meaning they can't compress anymore. And at this instant, we have the same velocity. If you look at one of the previous examples, it's exactly what was happening in that example. When you had the maximum compression of these particles, remember these particles are deformable. They are non-rigid. Okay, they can be compressed, they can be stretched. So they're coming at each other, they impact, they compress, and they're applying equal and opposite impulses. Then they have maximum compression, maximum deformation, and at this point they've got the same velocity. Very important. Then they begin to restore, just like a spring restores after maximum. Okay, restitution impulse. They begin to apply an impulse on each other again, called the restitution impulse, equal and opposite. Okay, plus restitution impulse minus restitution impulse, and then they separate. And after impact, we've got different momenta. We've got different velocities, a different velocity after impact for A and a different velocity after impact for B. Okay? So this is what is happening during collision, during impact. They come at each other, they collide, they have these impulses, they keep deforming to a maximum deformation, then they have the same velocity, then they begin to restore, okay, and they have a different impulse to integral of P, they've got integral of R, Okay, then they separate and they've got velocities after impact. That is what is happening. We will use this information again to derive our coefficient of restitution. See you in the next video.